Some of the most powerful tools in science aren't the brand new, flashy ones. They're the classics. Today, we're going to talk about a technique that's over a century old, but is still at the absolute heart of modern analysis. It's called potentiometry, and it's basically the science of measuring things you can't even see.
Seriously, just think about it for a second. How would you figure out the exact amount of salt in your soup? Or say the active ingredient in a pill without, taking it apart molecule by molecule? It sounds kind of impossible, right? Well, it turns out there's a really elegant electrical solution to this exact problem.
All right, so here's our game plan. First, we'll dig into this whole challenge of measuring the invisible. Then, we'll get straight to the point. What even is potentiometry? After that, things get fun. We'll meet the electric detective duo that makes it all happen. We'll see how they find the crucial tipping point, and then, the best part, we'll see how this goes from a lab bench right into your life. Okay, let's jump right in. The fundamental problem. How in the world do you measure something you can't even see? I mean, think about almost anything. Your blood, a glass of juice, even a sample of river water. It's basically a chemical soup, right? A huge mix of all kinds of stuff. And the real challenge is trying to find and measure just one specific ingredient, one type of ion, which is just a tiny charged particle, in that super crowded mixture. You need a tool that can somehow ignore all the other background noise and just zero in on the one thing you care about. Well, that tool is potentiometry, and it's so clever. It's a method that takes a purely chemical property, like how much of something is in a solution, and translates it into something super easy for us to measure, an electrical voltage.
Now, we're not just talking about measuring general electricity here. No. Potentiometry is way more precise than that. It uses a really specialized setup to measure what's called electric potential. You can kind of think of it like electrical pressure. And the key is this pressure is created by the one specific ion we're looking for. That's why it's so powerful. It's targeted, it's selective, it's a laser beam, not a floodlight.
Okay, so here's the absolute core idea, and it's actually pretty simple. The more ions you have, the higher the voltage. The fewer ions, the lower the voltage. It's a direct, predictable relationship. That's the magic trick. Now, there's a fancy formula for it called the Nernst equation, but you can just think of it as the Rosetta Stone, the universal translator between the language of chemistry, concentration, and the language of physics, voltage.
So how do we actually, measure that voltage? Well, it's not as simple as just sticking one probe in. You actually need two. And I want you to think of them as a team, like an electric detective duo, working a case together to get their answer. And they have very different jobs. First up, you've got the indicator electrode. This is your on-scene detective. It's the one doing the real work. Designed to be super sensitive, responding directly to the ion we're measuring, its voltage goes up and down with the concentration. Then you have its partner, the reference electrode. This is the steady partner. Its job is to be boring. Its potential is known, it's constant, it's totally stable. It's the reliable baseline that everything gets compared to. So a simple voltmeter comes in and just measures the difference between our sensitive detective and our steady partner. And think about it, since the steady partner's voltage never changes, any difference we see has to be coming from the on-scene detective reacting to the ions. That difference, that little number on the voltmeter, that's our answer. It tells us the concentration. Now, to be that reliable, steady partner, a reference electrode has to be pretty special. You can't just use any old wire. It needs a known, rock-solid potential. It has to stay constant. And most importantly, it has to be completely uninterested in whatever else is in the solution. Some common ones you'll see in labs are the calomel and the silver-silver chloride electrodes. They're basically the gold standard for stability. Okay, so now that we've met our detective duo, let's see them in action in one of their most powerful applications. It's a process called potentiometric titration. And this is so cool because it's not just about taking a single snapshot of what's there. It's about watching a chemical reaction happen, step by step, to find its exact finish line. So here's how it works. It's very methodical. You take your two electrodes and you put them into your sample. Then, very slowly, drop by drop, you add another chemical called a titrant. And the key is, after every single drop, you take a reading of the voltage. You're just watching the numbers. And what you're looking for isn't one specific number, but a sudden, dramatic jump.
Yeah, there's a great line in the source material that really nails it. It talks about how this sudden change in potential reveals the endpoint. And that's exactly it. For most of the time, the voltage just creeps up slowly, very predictably. Then, bam, it skyrockets. That jump isn't a mistake. That's the signal. That's the finish line you've been hunting for. If you were to graph this, it would look like you're walking up a gentle hill that suddenly turns into a sheer cliff, or like the edge of a waterfall. That super steep part of the graph is what scientists call the equivalence point. It marks the exact moment that the reaction is perfectly complete. And because you know exactly how much of that titrant you added to get there, you can work backwards and calculate the original concentration with amazing precision. Okay, so I know this might all sound a bit like abstract chemistry class, right? But I promise you, this technique is working behind the scenes all around us every single day in ways you probably don't even realize. Let's just talk about the food you eat. That salt content listed on a package of bacon, potentiometry. The amount of calcium in your milk or potassium in your juice, potentiometry. It's even used to make sure preservatives, like nitrates in salami, are at safe levels. It is an absolute cornerstone of food quality control. Then there's medicine, where it's just as critical. It's used to verify the purity and the exact dosage of medications, like the antibiotic amoxicillin. And hey, have you ever heard of a pH meter? Guess what? That is potentiometry. And when you use that to measure the pH of blood, that simple test can help doctors diagnose really serious conditions like acidosis or alkalosis.
And the list just keeps going. We're talking about environmental safety, monitoring for nasty stuff like cyanides in wastewater. It's a key part of big industrial processes, like making bleach for the paper industry. Geologists even use it to figure out what's in petroleum. Honestly, it is everywhere.
And here's what's so wild to me. This isn't some brand new cutting-edge discovery. Potentiometry is a classic. It was developed before the 20th century. We're talking over 100 years ago. And yet, it is still an absolutely essential tool in labs all over the world today. Talk about staying power.
So at the end of the day, if there's one thing to remember, it's this. Potentiometry is our window into the invisible, dissolved world around us. It's fast, it's super sensitive, and most importantly, it's selective. It gives us the power to pick out one single ingredient from that big chemical soup we were talking about earlier. It's this incredible technique that literally makes the invisible visible. It quietly ensures the safety and quality of our food, our medicine, our environment. And that just leaves me with one final question for you. As our world gets more and more complex, what are the next invisible things we're going to need to learn how to see?